So today is the sixth time we're meeting, and we're going to discuss more about material properties. And we will also go back to the lab to do another experiment with aluminum. What did you all think about the lab yesterday? Okay, yeah, it was interesting, right? Hopefully, maybe a little bit. We got to see the stress strain curves, or at least the force displacement curves, which go into the stress strain curves. Did anyone try taking their data and putting it into the Python script yet for the lab? Okay, not yet. Well, we'll it'd be good if we had some time to do that. I don't know if we'll have time to do that today, but there are videos under the all the sessions called under what's called lab, and then you can watch them and you can process your data. Okay. The data you were getting, I didn't do a careful analysis, but it looked pretty good. A lot of you were quite proficient at being able to get a nice continuous looking force displacement plot. So thank you for your participation, and we'll go back to it today. On Monday, we have exam 1 in the class. Okay, so that's exciting. That will be here, and we have an opportunity to work by ourselves, of course, and please bring a sheet of notes. Anything you want on the notes, previous problems, anything, okay? Try not to, it needs to be handwritten though. Okay, it needs to be handwritten, and yes, if you have a digital device that lets you handwrite on it and you would like to print it, that's fine. You're not going to use a digital device, of course, during the exam, but anything you want to write is fair game. Okay. Yes, Dylan.
Is it like to be 1 or 2 sides?
Oh, two-sided, yes. 8.5 by 11, or A4, I believe, is the equivalent European or other international standard. And yes, both sides. Okay. And then, of course, some people ask, can I use all 6 sides? Sure, fine. If you want to use all 6 sides, it's fine. Okay, any questions on that? That will be essentially the full length of our class on Monday. Now, a couple of other things. Today is Tuesday, of course, and so we have an assignment due tomorrow. And then Wednesday, we'll have an assignment that we get for Thursday. And on Thursday, the assignment will not be due, excuse me, or the couple of modules will not be due until Tuesday after the exam. Nonetheless, if you look at the syllabus, all right, what I decided is that exam 1 would cover essentially halfway through Thursday. Okay, so today's session 6, tomorrow's session 7, and then Thursday we have sessions 8 and 9. The exam will cover through session 8. Okay, that seemed to be a little bit more of a nice place to break things up for me, okay, at least when I was looking at it. Okay, so any questions on that? So you won't have an assignment, you won't have any assignments due on Monday, but you are responsible for the material in session 8. Okay, and session 8, though, that corresponding assignment will be due on Tuesday. Okay, so hopefully you have the weekend to kind of study, and Monday morning, and you come in and you hit it, all right? My personal advice, these types of exams are ones where I think I would weight sleep, okay, above cramming. Okay. Now we haven't covered that much material, so hopefully, it's about doing some practice problems, but when I take exams, I would weigh, okay, do I have to remember a lot of things, or do I have to be able to think on the fly? And usually, if I can think on the fly, then I sleep. If it's a lot of memorization, then I say, forget the sleep. I'll just stay up and I'll just try to cram more information in my head. Okay, but everyone's different. And you have a formula or a sheet of notes, front and back. So hopefully the memorization won't be that tricky. But you'll want to be populating that sheet, probably pretty soon. Okay. Great. Oh yes, and I've mentioned it to some of you, but you have, I think, 6 or 7 exam 1s that you can look at on the website. Start with the most recent ones and work backward. That'd be my advice. 2015, 2016, I was kind of cruel. It's still there for history, but the exams were pretty brutal. I think they've become a little more, how do you say it, evaluation of concepts without kind of nailing some of the trickiness, okay? Okay, so let's go ahead and get started then, unless there are questions. Yesterday, we spent some time covering material properties. In particular, we discussed the stress strain curves of the materials that we're most interested in, which primarily include things like aluminum and steel, but we also discussed that the parameters and the different attributes of stress strain curves that we look at are relevant to rubbery materials and polymers. They're also relevant to the brittle materials like ceramics and glasses. In particular, right, we said that brittle material is not going to have as long of a plastic regime. Today we're going to discuss a bit more on ductility. We're also going to models. So you already have this idea of what the linear regime is for material and what the plastic regime is. And we'll discuss this other model. I think, Kira, you asked, well, isn't there kind of sometimes another slope there? So we're going to talk about that plastic, the slope in the plastic regime that you can use sometimes. We'll discuss modulus of resilience, modulus of toughness, which are attributes that we want you to be able to calculate or use Python to calculate for the lab. Okay, if you took a look at the lab, you'll see that that's part of the opportunity to learn. We'll talk about Poisson's ratio, and we'll get into a little bit of a general approach, okay, to mechanics. Now, this is supposed to be a review slide, and it kind of is, right? So we talked about tensile and compressive tests, we talked about stress-strain relationships, we talked about elastic modulus, we talked about uniaxial failure, but one thing that we didn't, I said, we'll talk about it tomorrow, that we didn't talk about too much was residual strain, okay? And maybe it's better if I just draw this from scratch, okay? So where do I do that? Let's do it right here. Okay, so let's talk about residual strain. Okay. Now, what is a residual? Well, residual, you can think of it as something that's left over. It's the leftover, all right? In mechanics, or in design of mechanical components, you'll talk more about residual stresses and residual strains in the context of structure, like a beam that can have kind of some regions that are going to be in tension residually and some are going to be in compression residually. But today we're focusing on the bar, okay, on uniaxial loading. So if I have a stress strain curve that looks kind of like this. Whoops. I don't know what it's doing. Kind of like this. I didn't like that, okay. You tell me, what are essentially the two attributes? Well, you could argue there are other attributes, like I could put units and stuff, but if you're looking at this, what are kind of two of the parameters that you would be interested in seeing? Or maybe three parameters that you'd be interested in seeing on a stress strain curve? Yes, Andrew.
The elastic modulus?
Yes, so you would want to see something like an elastic modulus, right? So sometimes we write it like this, even though there's no way that we're going over 1. Right, that's like 100%, right? But anyway, we get the idea, right? That's the elastic modulus. What else? Yes, Dylan.
The elastic limit.
Okay, so yeah, so the elastic limit, which I said we're not going to think about too much, although it will come up in a minute, or the proportional limit and elastic, and we'll talk about them. But what do we use instead usually? We say that it's all lumped together.
Yield strength.
Yeah, the yield strength is usually what your material providers are going to provide, or you're going to specify. Okay, so yes, I agree. There's like this proportional limit. There's this elastic limit. There are these. If I want, I can like kind of draw them in there, but we don't really care about them so much. Okay. Like yeah, all right, stuff like that. But it's really the yield strength. Now, this is a linear elastic, perfectly plastic model, and something I didn't tell you yesterday is that if you go beyond the yield strength and you go over to the right, okay, remember I did tell you that it's going to, if it's perfectly flat, that suggests that you're getting a free lunch. In other words, you just get more and more strain without having to increase the amount of force. Okay? It's not really a free lunch. It's just not, there's no longer a significant slope. Okay. So let's say you get out to here. Okay. Actually, let's not put an X there. Let's just put a, because X often is used for braking. That's like where it breaks. Okay. So we get out to that location. And then we let go. We do like an Elsa. All right. So what happens when we let go? So what I'm saying, what do I mean by letting go? I mean literally, if I were to like release one of the ends in the tensile testing machine, all right? What do you think is going to happen? Yes, Kavya.
It'll like go back a little bit to its original form.
Yeah, exactly. It will go back a little bit to its. That's a very well way to put it. Okay, okay. And any idea how I calculate how much of a little it will go back to its original form? Any guesses? Yes.
Would it be like this direction, flat line?
Okay, so that's a good guess. You'd be like, all right, so maybe I go from here to here, right? Okay, that's a good guess. Now there's a thingy though there. If I go from here to here, that still suggests that there's a lot of force divided by area, stress in the material. Okay, when I release it, I let go, right? There's actually no longer any stress in the material, okay? But there is going to be residual strain, okay? All right, so that's a good idea. So like we could move this way. Any other guesses? Dylan, yes.
Would it like follow the path of the slope from the Young's modulus?
Bada bing, bada boom, you're right, okay? So what happens is that it goes down like this. Okay. So when you unload it, it will return along with the slope, okay, of the elastic modulus. All right, so if there are a few things here, right? So let's say that you got out to this point. We'll call this, I don't know, applied. Epsilon applied. Okay. And let's call this, since this is the yield strength, we'll call this epsilon y. Okay, so that's like the yield strain, right? The yield stress or the yield strength is the vertical, right? That's in megapascals typically. The yield strain is going to be dimensionless, unitless. Okay? So this epsilon y is the same as the epsilon y here. Do you see that? All right, so this distance and this distance, they're the same. Okay? Now, what do we think of epsilon residual? Residual, we kind of say it's the leftover. The way we define residual is like that. So epsilon residual, this is the residual. My handwriting is poor, but it's generally legible. Okay, residual strain. Okay, and we get, I can't even say it quite like you said it, Davia, but it's like it comes back almost, or it comes back a little. What did you say? It's a little bit come back. Yeah, it comes back a little, right? So it's possible. All right, now this may be slightly exaggerated, right? But it depends. It's possible that you actually have residual strain that's greater than the epsilon y. It's also possible, okay, that if, let's say we only went out to this point over here, it's possible that the residual strain is less than epsilon y, okay? So residual strain can be greater than epsilon y, or it can be less, right? What it depends is, this is dependent on, or this depends, let's put it this, depends on the applied strain. Any questions on that? Okay. Another thing to keep in mind, this is a second concept that we didn't talk about. All right, so let's just let me see. Can I even draw on another color? I don't know if it lets me. You should know how this works by now. Let's see. Oh yeah, let's try a different color. All right. So another concept and rule, which is kind of unrelated but similar, okay, is approximation. We'll call this how to approximate. Oh, now that's awkward. That's very awkward. What do I do? I would say, okay, how to approximate the yield strength from data. Okay. So as you saw yesterday, sometimes when you get these force displacement curves, or then you convert them to stress strain curves. So again, this is stress versus strain, right? And we said, if you've ever used versus, make sure the first thing before the versus is the y-axis, and the second thing after the versus is the x-axis. So a lot of times what happens is you'll get data that look a little bit like that, right? You remember that? That's kind of how it looked. And then actually it kind of came down too, right? It broke. Okay. That's not the best this. Okay, so if I ask you, okay, the ultimate tensile strength, right, that's just going to be the maximum value on the plot. So that's pretty simple. But if I ask you, where is the yield strength? Well, some of you would be like, well, it looks like here. I know, maybe it's more like here. Maybe it's like over here, okay? But there's a general kind of approximation that's called the 0.2% offset method. Yes, thank you. Okay? And the way this works is you go I'll say I don't know, let's just do this. We go like this, 0.2%, okay? And then we use the slope, so we can calculate the slope right here. We use that same slope, okay? And wherever we hit, this is now what we call the yield strength. And if we want, right, this is what you can consider to be the yield strength. Okay? It's just an approximation. It's not necessarily it's not necessarily always accurate, okay, and the manufacturer might pick something else, but this is kind of a rule of thumb if you have stretch strain data. Any questions? So they're similar, but you see they're completely different concepts in a sense, right? But they both make use of the slope that we have associated with an elastic modulus. Okay? Any questions? All right. And so now this is a little bit more prefabricated slide on that. And this slide is just telling you what some of the yield strengths of common materials, or maybe not common materials, that you have around the house. Kevlar, right? Why do we like it? Because it has an extremely high yield strength. And it's often not used by itself. I guess in fabrics, in fabrics it can be, it's still kind of there, but a lot of times Kevlar, carbon fiber, glass fiber, they're used in epoxy composites, and we've mentioned that before. Steel can have a very high yield strength. And what is high? I mean, when you get over 1,000 megapascals, when you hit the 1 gigapascal mark for yield strength, I consider that to be extremely high. Normally, I'm thinking that whatever type of yield strength I have is going to be less than 1,000. Like hundreds of megapascals is what I think of for yield strengths with aluminums and steels. In DMC you'll talk more about, and also MechProps, you'll talk more about what can influence the yield strengths of particular materials. Just one really cool thing though about steel. Steel, as we mentioned before, can come in different compositions, but its elastic modulus stays the same, as we also mentioned before. What I didn't mention too much is that the ways that you can change the yield strength are often synergistic with where the maximum stresses are going to occur. So this is really neat. Often when you have a beam that bends, and we'll cover this, or when you have a shaft that twists, we'll cover this, the stresses that are greatest are at the outskirts, at the surfaces, near the surfaces of the materials. Well, it turns out that we can either plastically deform the material, okay, and cause its yield strength to go up. And how do you plastically deform a material? You could just, for example, hit it on the outside. This is like shot peening, essentially, is a bunch of balls being fired at it, and it induces a lot of like little divots, and that increases the strength on the outside. Another way is what's called quenching. So you take the material, like steel, you heat it up quite a bit, and then you just have a bucket of water, and you take that very hot material, and you take it out of the furnace, and you put it in the bucket, and that quenching behavior actually causes that quenched material that is cooled very quickly to harden or to have a higher strength. So steel is magnificent because you can change the strength of it just by heating and cooling, or even stressing it plastically, and it's often at the outsides of the material where that is most prevalent, and that's where the stresses are often the highest. So there's this very nice synergistic behavior. Okay. Copper, soft material, right? Anyone dealt with copper wire or any type of copper material? on the softer side. And okay, so I should be careful when we say da 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 da. What's the difference between? Well, actually, maybe the next couple of slides we'll talk about this. But is there a correlation between hardness and elastic modulus? Yeah, often, right? In order to be a very hard material, you're probably going to have a pretty high elastic modulus. Okay? But hardness is actually it's not quite yield strength, okay? But it's often a metric that we use for strength. So just like we talk about, we just try to put a chunk of material in a tensile testing machine to measure its material properties, okay? If you have a structure, if you have a structure, okay, for example, when I was a grad student, I got to do some, quote, consulting for this professor. It paid really, really well. When you're a poor graduate student and you don't have much money, it made a huge difference in my family's life. I was so grateful, okay? But anyway, one of the cases we had was where, and then of course, he would bill my hours and then put something on top of it, so he'd still get paid no matter what I did, right? And then he gets paid a lot of money. So, so one of the cases we had was someone had gotten injured. This is often the way a lot of these cases work, and so there's litigation involved, and you have these expert witnesses, and they're weighing in on different things. So there was a bar, one that you would use for bench pressing, okay? And we had this sample, and it had been, and somehow the individual got hurt. And I think there was a claim that the bar had bent or it had broken in some way, okay? So we actually got one of these bars. I don't think it might have been the actual one, I don't remember though. And we would do these hardness measurements. So often there's a very nice Vickers or Brunel hardness machine, and you have this little ball that comes down and you press in and you measure what the size of the indentation is. But they also make these portable machines that you can again push a ball or some type of hard surface into the material, and then it measures how deep it goes, and that's going to give you an idea what the hardness of the material is. Okay, so anyway, so we went around on the bar, and we're just measuring the hardness, and then we're correlating that hardness with what the strength of the material was. Okay, say, hey, yeah, this makes sense. This doesn't make sense for why it would have failed here or there. Okay. Okay. So and then silicones, they have very low. So we have polymer, and we have then more metal. So tin is a nice soft material, and can be used for a variety of applications, and it can be used kind of like lead. Lead is actually a very nice material too for its product. That's why it was used for so long. Still used in a lot of applications. Has anyone ever used leaded solder versus unleaded solder? Maybe you're too young because they probably don't. It's probably harder to buy leaded solder now. But if you ever use leaded solder, boy, it is so much easier to do your soldering. There was one time I was like, that's leaded solder, dude, in the lab. He's licking it. I'm like, dude, don't lick it. It's leaded solder, right? The fumes are going out, right? Yeah, this is over a decade ago. This is a long time ago. All right. So, but anyway, but yeah, the reflow and some of the properties of lead are quite nice. But yes, of course, we should not use it for health reasons. Okay. So we talked about residual strain, talked about these things. All right, this is good. We draw the line. Da 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 da. Yeah. Okay, we got that. All right. I don't think I'm going to talk about it. Well, I'll wait to talk about it. There's another cool thing that I can show you. All right, but we'll talk about it in just a minute. All right. So a ductile material. We've talked about ductile materials already, but here's a definition. This is the degree to which a material, or the ductility you could say, is the degree to which a material can sustain plastic deformation under tensile stress before failure. Okay? And it doesn't necessarily have to be tensile stress, you know, it could be like a combination of things, but essentially you're going to have deformation, and it's not going to just, as soon as it starts to deform, right, it's not going to like snap. That's right, that's a brittle material. And in this idea that you are able to have plastic deformation, okay, we have this toughness, which we'll talk about. But before you start to go plastic, we also have something that we think of as resilience, okay? And resilience, a brittle material can have it as well, but resilience usually refers to, or the modulus of resilience in particular, which we'll talk about in a second, usually refers to the amount of energy that is stored in the elastic regime, okay? But ductility often does refer to what happens in the plastic regime as well. So there are two ways to report ductility, and it's based on failure analysis, okay? One is, what is the final length minus the initial length, all right, divided by the initial length. So this ratio. So it's like a percent elongation. And the other is what we call a percent reduction in area. So the initial area, cross-sectional area, minus the final cross-section area over the initial. Okay, and like you can times 100%. So these are kind of two ways that we report ductility after completed failure. Okay. So these materials, they neck, all right? And this is not like another type of necking. This is professional necking, okay? And this is what it might look like, all right, after it's gone through this long plastic deformation. A brittle material, on the other hand, okay, will typically have a flatter and even maybe rougher surface. Okay? And if you can see, like, the cross-sectional area hasn't changed that much, and there hasn't been much extension either. Okay? And so we kind of discussed this a little bit yesterday, at least in terms of the stress-strain curves and what they look like. And so this resilience, all right, you can see that in the plastic regime, a ductile material has all this area under the curve, and we're going to talk about that area under the curve. But that area under the curve gives us some idea of the ductility that a material might have. Okay. Yes, and that's just a way to calculate it, okay? And another way to calculate it. All right, so there are going to be two models that we're responsible for in this class. Okay. One is the linearly elastic, perfectly plastic model, and this one is the one that we've already discussed. It goes up, and then it goes flat. Okay. And what is this? This is going to capture a number of things. It's going to tell us the elastic modulus. It's going to tell us the yield strength. Okay. It does not capture ultimate tensile strength, and it does not capture what's called strain hardening, which we'll talk about a little bit in a second. It does capture plastic deformation, okay? And essentially, the maximum stress is just the yield strength. Okay, so if you say, or if I say in DMC, when you take it, with whomever you take it, and they say, okay, this is a linear elastic, perfectly plastic material, and I have a strain of 0.5%. That's a lot for a steel. What's the stress under loading? Immediately you say the yield strength, okay? Because that's the max. It can't go higher than that with a linear elastic, perfectly plastic model. You can use it for calculating residual strain from unloading, which we just showed you how to do. Now, the linearly elastic, linearly plastic model, okay, is another simplified model, and it's like, and it's almost kind of trying to be like, just give me the plot. That's the simplest thing. No, but if we want, when we say simplified models, right, a plot has lots and lots of data points on it. Here, we're essentially able to parameterize a linearly elastic, perfectly plastic model, right, with just two, elastic modulus and the yield strength. Okay, and maybe you have like the strain at the final, you know, the strain at the break. Okay, in linear elastic, perfectly plastic, you know, you have a couple more parameters, but you don't need like, you know, the 1,000 data points. I mean, your data yesterday, right? I don't know how many. It was sampling at 50 hertz. We didn't talk about that really, right? That's 50 data points per second. And, you know, it would run for, like, you're running for, I don't know, 30 seconds? Okay, so that's like 15,000 data points. Or 1,500 data points, okay? So linearly elastic, linearly plastic, strain hardening. Okay, so what are they talking about? All right, or what are we talking about? So first, that's the linearly elastic, right? So you can say, okay, linearly elastic, boom. Perfectly plastic, boom. Linearly elastic, boom. Linearly plastic, strain hardening. What does that mean? It means it goes up, okay? The slope of force is much less. We talked about that yesterday as well. And it does not capture the ultimate tensile strength because it just keeps going up. But it does allow us to capture, what is this? Strain hardening. So what is strain hardening? Strain hardening is actually related to what we were talking about with being able to apply a load like a shot peening with the balls, or being able to deform the outer surfaces of materials to make them stronger. What happens in strain hardening is this. You go up, and let's say we're using our linear elastic, linearly plastic model. You hit the yield strength, try different colors, fun. Okay, so you're going up, you go past the yield strength, and say you go up here. Okay, you go to this like pretty high epsilon applied. Okay, so based on what you know, or what we discussed a few minutes ago, where, if I now release the load, where will I end up? I let it go, I can't hold it back anymore. Where do I end up? Yes?
You would follow a slope parallel to the initial linear format.
Yes. Okay, so we don't use the slope here. Okay, I'm sure there's someone that probably has some proposed model that is like in between these two, but we use the slope that's over here. Okay, and so this is a rough idea of what parallel is. That's not so bad. Okay, and so we end up over here. Okay, and then this is our new residual strain. So we have to calculate. So this is a little bit tricky, right? It says like if someone says, I've applied epsilon applied, you gotta be like, oh darn, it's not that simple because I have to go. I have to know that I've already gone this far. And then I gotta keep going. I gotta figure out, okay, now this next slope, how much further up am I, right? Because this sigma applied, right, is going to be dependent on this triangle as well, right? So to figure out how far down we go, right, you've got to know the kind of this height, or you got to figure out how much further up from SY you've gone. And then you can figure out how that will help you with the epsilon applied. All right. So anyway, or maybe they give you epsilon. They could give you a sigma applied or epsilon applied, right? Either one I can give you, right? But you got to be able to figure out where in the world you are on the stress strain plot, and we'll go over how to do that in a little bit. Why is this strain hardening? Well, something magical happens, and again, you'll cover it more in probably mechanical properties of materials. what magic will happen, the magic. I hate, it's like, is this a technical class? Magic. Material is now stronger. What does that mean? That means that, okay, now I'm back down here. I let it go, all right, and Anna pulls me up and stresses me out, okay? But guess what? I don't yield at the old yield strength. I don't yield until I get to that new yield strength. Okay, so this is now your new, or we'll call it SY new. Okay, and this is what straight hardening is. This is how you actually get more strength out of a material. Okay. You know, it has its limits. Right? You can't just like strain the thing out of its mind. Okay, but this is the general principle. This is the general principle. Any questions on this? Okay, so, oh boy, I'm going too slow again. All right, so in this example, okay, we have a linear elastic, perfectly plastic material with an elastic modulus of 210 gigapascals. If I say 210 gigapascals, who do you say the material is?
Steel.
Most likely steel. All right, it could be something else, but that's steel, likely. Okay. It has a yield strength of 200 megapascals. You say, oh, okay, that's just some material. Right? It could be all kinds of steels. Right? I don't know which grade it is. Someone else will probably know. They could tell you probably the heat treatment and everything they get there, but I'm sorry, I'm not there. If we strain the material to 0.3%, what will be the residual strain when the load is released? All right, so we kind of already did this. We go up that slope, and we get to, or we go through the linear region, we then get to the strain associated with the yielding. Okay, so this is the strain at onset of yield. Okay, so epsilon y, and this is kind of fun. So this epsilon y is just going to be sy divided by e, right? Because sigma is equal to e epsilon. All right, so then if I want epsilon y, I just say, oh, okay, I'm just going to divide both sides of this equation by e. And that will tell us what? It'll tell us how far we are over to this point. Okay, so we've now progressed to 0.095%. We were going though to 0.3%, so we go further. Okay, so we go out to here to 0.3%, and of course it's flat and level. And now we need to figure out the residual strain, which is going to be based on going back down the elastic modulus line. All right, and that's a 0.095%, right? That's the same as this, the green to the pink, right? So this purple, or this intersection of the purple with the x-axis right here, and this pink is going to be, again, that 0.095%. So then you tell me, what is the residual strain? What is the residual strain? Yes, Joshua.
0.205.
Right, so it's going to be the difference, right, between 0.3% and 0.095, and that's just going to be, we can say the epsilon max minus epsilon y, okay, and as you said, it's 0.205. Okay. Questions? You want to be able to do this, all right, and it's like, again, there are these like little things we can do. This case, we said we're going to apply strain of 0.3%. Okay. Maybe we would. Oh, we kind of had to tell you how much. Okay. Or maybe tell you the residual strain, and we tell you, hey, what did you go up to? You know, what was the maximum flush? Right? So like, they're just little things you can play. Or maybe I won't tell you the yield strength, but I'll tell you the yield strain, right? And then you can calculate what the yield strength is. If I ask you, hey, what stress did you get to in the material? Well, I got up to the yield strength, or yield strength. Okay. Okay, good. So there's some homework problems on this. Okay. There's some more homework problems, and you can review previous exam ones if you like. Okay. This was during a COVID exam. Okay, so our exams are not going to look like Canvas. Okay, they'll look more like the other ones, but you know what we're going to do. We had to write exams in Canvas for a little while. Okay, now this is more complicated. This is a linearly elastic, linearly plastic material. Okay, so in this case, you have an elastic modulus, again, of 210 gigapascals, a yield strength, again, of 200 megapascals, and then we say there's a strain hardening slope of 20 gigapascals. Okay, often we might, slope S is not necessarily the best because often I use S, like S sub Y for yield strength, but anyway, that's the slope in the plastic regime. So we go up, all right, to epsilon y, and then we keep going, all right. We don't know exactly where this is. This is just some like high stress, okay, associated with this epsilon max. Okay. Well, I know I can calculate this strain right here, okay, which means, all right, I know, because how can I calculate? Because I know I'm yielding, right, and I just know that this epsilon y is equal to the yield strength, which is 200 megapascals, divided by 210 gigapascals, the elastic modulus. So now, right, I can figure out, hey, how far did I go? How far did I yield, okay, in the plastic regime? Because they gave us the epsilon max, that 0.3%. Okay, so if I know how far I went and I know the slope, right, then I can figure out how high up I went as well. Okay, so the new stress, right, is going to be this SY, which is 200 megapascals, or sigma y, whichever you like, and we're calling it then this delta right here, this between this dash line and this point. We're calling that, I'm just calling it, I was being cute, I guess, the S nu v. All right, and that's going to be, that's why, this is why slope S is confusing, but slope S times this X, right, will give us the Y. And so then from there, we can figure out what the new yield strength of the material will be. This is from strain hardening, right? So like, if I let it go, right, this would come all the way back down here, and we have a material with a new, very high strength. Okay. We can also calculate the residual. Okay. And this is more complicated as well, because what we need to do is we need to go all the way to epsilon max, right? And then we need to take S nu, this new strength, and what do we divide it by? We divide it by the elastic modulus, right? And this, right, so this distance between this purple intersection and this pink intersection of the axis is larger, doesn't maybe look like that, but this is larger than this green to pink over here. Okay, because we went up higher. We had to go up higher, and so we had to go down. So in this case, the residual stress is a little bit different, okay, than what we calculated before. Any questions on this? No? It's intuitive when you see it step by step, I think. It gets a little trickier when you're seeing a word problem that's just slightly different than what you've seen before. Okay, so You wanna like think about what could one ask? What are the different permutations that can be asked about these types of problems? Okay. All right. Let's keep going. Modulus of resilience, modulus of toughness. All right. So you're familiar with this. We talked about this, right? Yesterday, I think Shane said, "Hey, the energy in a spring is 1/2 k delta squared." And I said, absolutely, I agree with you. Or 1/2 kx squared, I think you said. Okay. Well, something that you may not think about is because we often think in terms of the spring constant when we're talking about the energy stored. But another way to think of this is to take the force, whatever that force is, times the delta and divide by 2, right? That's the same thing. It's the area under the triangle. This is for a spring, right? So, you go back, F equals K delta. We can figure out what the energy is, which is 1/2 K delta squared, but also, we can think about it as 1/2 times the force times the displacement. What are the units here? What are the units for energy? For the work, external work, or for the energy stored in a spring? Yes?
Joules.
Yeah, joules, right? So newtons times meters, right? And so this is also reassuring. Newtons times meters, maybe, or force times distance. Okay, now, what do you think about this equivalent idea, but not with a spring, but with a material? And we're going to go back to our material element. So now, let's say that we have some stress acting on a material element, and it's infinitely small or infinitesimally small, and we have a delta x, delta y, delta z. Okay, we can think about a cross-sectional area. We can think about a force associated with it. We can think about a vertical displacement, right? We can make all these calculations now based on what we know for axial loading, right? This is one stress being applied, one normal stress. Okay? And so then if we begin to think about energy, okay, or the change in energy, right? And we think, oh yeah, we had this like 1/2 force times displacement over here. Okay, we can say, oh, there's, what I've done here is I've said, okay, this is actually just a chunk of material. This is actually just a spring, but we have really small dimensions on it with really small forces. Okay. And so we can say, oh, energy is energy. So the change in the energy here is going to be the same equation that we had over here. Okay, so now we can talk about this internal energy. Okay, so what is delta F? Well, we said delta F is sigma times delta A, right? What is delta A? Delta A in this case is delta X times delta Y, right? So this quantity in the first set of parentheses is it's the 1/2, and the delta F, and the delta F is the sigma times delta A, right? We see that? Sigma, delta X, delta Y. What is this delta? Well, the delta for this element is going to be, like we said, it's going to be epsilon times delta Z. That's just the, right? That's the relationship. Remember we said strain is just a delta over length, right? Some change in displacement over the initial length. So, right, we flipped it here. And we're saying that the strain times that length is going to give us the delta. So now this is the internal energy for this little element. Okay. Another way to write this out, if it goes forward, all right, is as such. We have, you see this? We just rearranged things. We have 1/2 sigma epsilon, like this, and then we have a volume, a small volume, delta X times delta Y times delta Z. So this change in, this is energy. So the units here, okay, if we think about them, they're the same units that we had previously. It's joules. Okay? It's just joules or it's Newton meters. But how do we, okay, and then we can write it like this, but how do we typically think of this? We think of it as not having a volume, okay? And so, or it's for a material, right? So what do? We're gonna do some division, right? So we go and we say, this is the strain energy on a given volume, and we're gonna divide the volume by both sides. So we have a delta U over delta V now, like this, and we actually call it a strain energy density. Usually, often I'll just say strain energy, okay? But it's really a strain energy density. I'm a little cavalier here. So the strain energy density, okay, is per volume, like you saw, we just divided by volume, and that's 1/2 sigma epsilon. If we say that it's a linear elastic material, well then sigma is equal to E epsilon. Okay, so epsilon is equal to sigma over E. So now we can write different relationships, like you could say, oh, I'm going to have 1/2 sigma big E, or I could have 1/2 E times, like, E times epsilon squared, right? If you substitute that way, or if you substitute this in on this side, then you get this equation right here. The elastic strain energy density is 1/2 times sigma squared over big E. Okay. What is this really telling us? Well, let's go back to the strain, the stress. Oh, okay, so here's some units. Yeah. Okay, actually, this is kind of important. So delta U was newtons per meter, or Newton meters, sorry, not newtons per meter, and delta V is meters cubed. So in the end, the units end up being newtons per meter squared, all right? Or you can just think, right, it's a strain energy density, right? So it's joules divided by meters cubed, essentially, right? Or some amount of energy divided by volume. Newtons per meter squared, right? This is kind of, I mean, it's kind of fun. This depends on being pascals. And that's nice because you know that sigma is in pascals often, right? And epsilon is dimensionless. So again, the units work out, okay? Now, what does this quantity mean in terms of a stretch strain plot? Well, I said we don't care about proportional limits so much. And we don't. So we'll normally just substitute Sy, or the sigma y, and epsilon y here, okay? But this elastic strain energy density is based on the area under this portion of the stretch strain curve. Okay, and this is before it goes plastic. So if I come up to this point, right, I just go back down where it started. I should have done that. I should have been clear about that, actually. Maybe I wasn't super clear about that. Okay. You know, I was like, oh, hey, look, this is cool. Where do you come back down if you go plastic? But if you don't go plastic, you just come back down to 0. Okay? That's what it means to be elastic. Okay? You're like, it's like, I don't know, The Incredibles or something, right? I'm amazed at how Elastigirl, I think often she goes plastic, but somehow she comes back to original form. Okay? But this is what elastic strain energy density looks like on a stretch strain plot, and we often just use the Gill strength instead. Okay? What about, and we name it something. We name it the modulus of resilience. Now we said resilience earlier refers to ductility, right? And then we showed that sometimes when you think about ductility, you also include the plastic regime, right? Because there's all the energy that can be stored once you go plastic, and that's during the necking part of the pool. Okay, so modulus of toughness is what we use to look at the total area under the curve. Right, this is another metric. So what do? We just say it's going to be the modulus of resilience plus the area under the plastic regime. And this is where having a model, right, like the linear elastic perfectly plastic model, can be helpful to make these calculations. So if we look at this, okay, modulus of toughness is often given by UT, and modulus of resilience, all right, so T is for toughness, R is for resilience. Okay, that's how we simplify it. Okay. Any questions on this? Okay, so you can expect that you need to be able to calculate these quantities, right, on Monday. And to do that, I'm not going to ask you to use the trapezoidal method on the exam, right? I could actually make little boxes and say, can you count the boxes? And that tells you how to calculate the area, right? Like, oh yeah, or count the boxes, that's the area, and that's boom, right? That's not a bad thing. That's not a bad thing to be able to do, right? Or maybe you want to count the box, or maybe you want to make some estimates. But usually the way we do it is as follows. You say, hey, here is a model, either the linearly elastic, perfectly plastic model, or the linear elastic, or the linear elastic, linearly plastic model, all right? And we say, hey, calculate area under here for the modulus of resilience, calculate area under here for part of the modulus toughness, add these two together, that gives you modulus of toughness, right? So this is a rectangle, this is a triangle. I know you can calculate the area under these. Okay? If we have, and we'll go through this kind of quickly, behind. A little trickier here though, okay? If you have a linearly elastic, linearly plastic model. There are a couple ways to do it. One is a triangle, rectangle, triangle, okay? But my daughter in the car, this is great when your kids get to be like the age, right? Like they're learning cool things. Like, hey, what's the area of a trapezoid? I'm like, oh shoot, do I know the area of a trapezoid, right? Actually, do I know the area of a trapezoid now, right? And I'm like, well, isn't it like the average of the top portion? Like usually I think of trapezoids this way, right? So isn't it like, the average of the two like bases times the height? She's like, oh, I never thought of that way before. Cause like she had the equation, right? But she's like, oh yeah, I guess it is the average. And it is, right? So you can take this and this, take their average, right? And then multiply by this, and that will give you the area in the trapezoidal region. Right? So again, you should be able to do that. Okay? Or you can do two triangles and a rectangle, whatever you want to do. Okay? You want to be able to calculate the modulus of resilience and the modulus of toughness. Okay, and what do you know? There's code if you want it, okay? Available for this homework, straight from a collab in your home. Okay. Yeah, so modulus of toughness, all right, and let's see. Yeah, so if you're given this chart, yeah, this one's pretty simple, right? What kind of model does this look like? Or what model would you use here? You only got two. Yes?
So linearly elastic, perfectly plastic.
Yeah, linearly elastic, perfectly plastic, right? I like that. It's almost like a wrap. Like you could make a linearly elastic, perfectly plastic, right? There was a song from the 90s, I think, called I'm a Barbie Girl, something like that. Life is plastic, I don't know. Something like that, I don't know. Anyway, so, yes. Yes, so then again, what is the modulus of toughness? Okay, so you gotta do these. Okay, we're almost there. This is a lot. You know, I think I'm gonna cover this tomorrow, to be honest, because I want us to get back in the lab and not go too late. All right. So what we'll talk about tomorrow is how a material shrinks in its cross-sectional area as you pull it in the other direction. Okay, great. So any questions before we go over to the lab? No? All right, go ahead and give me a minute to pack up my stuff. Thank you for your patience.